the 2017 forensic excavation of Messerschmitt BF 109E-4. Werk number 1531 operates under strict legal boundaries. Authorized by Ministry of Defense License 1848, the recovery team arrives at an agricultural field at Townings Farm in Chailey, Sussex, near the broader Haywards Heath area. Their objective is to recover the remaining material footprint of a fighter lost on 28th of October 1940. The primary operational constraint is not a hostile remote environment, but a severely depleted debris field. This site has been subjected to decades of organized surface clearance and piecemeal salvage. Shallow crash environments in accessible open terrain routinely undergo sequential extraction phases. When an aircraft strikes an agricultural field, much of the airframe can remain accessible from the surface, allowing rapid clearance. Later accounts of the site indicate that a Royal Air Force recovery team removed the larger exposed items in 1940, clearing the field soon after the crash. Their focus was swift site clearance and safety control, not a slow archaeological recovery. They hauled away the most visible structural components of the fuselage and wings, leaving fractured material and buried fragments behind. This initial action removed the majority of the physical aircraft mass from the field. The site then entered a dormant phase, slowly covered over by routine agricultural activity. However, known crash sites located in accessible farmland remain vulnerable to secondary extraction efforts. In the 1970s, a later recovery effort is understood to have targeted the crater itself. Reports suggest this effort pulled the front of the engine and the propeller hub from the crater, and their present whereabouts are unknown. Those dense parts were obvious targets for unofficial recovery, and their loss removed the site's last heavy mechanical assemblies. Consequently, the evidence profile has already been rewritten by earlier recoveries. The 1940 clearance removed the exposed airframe, and the 1970s effort pulled out the remaining heavy mechanical prizes. What is left is a shallow, heavily disturbed scatter of fractured fragments and small sub-assemblies, with only the deepest pieces still beyond the reach of earlier machinery. That history dictates today's pacing and tools, controlled excavation, and systematic sorting designed to recover the small, contextual fragments earlier teams either ignored or did not recognize. Operating under Ministry of Defense License 1848, the team must treat this as a controlled forensic recovery, not a casual salvage dig. The license sets strict handling and reporting protocols so each fragment can be recovered with context and the loss can be documented accurately. Earlier interventions removed what was obvious or desirable. This phase is built to capture what remains, however small, without breaking the site record. The fundamental trade-off in excavating a previously harvested site is high operational effort for minimal intact structure. The modern team invests significant logistical resources to filter a highly disturbed upper soil layer. The agricultural setting means the ground has not been sealed under concrete or urban development. The earth remains soft, allowing water to percolate and heavy farm plows to churn the upper layers year after year. This repeated agricultural action mixes organic earth with oxidized aluminum, shattered fasteners, and fragmented wiring. The team must work systematically through this disturbed plow line to reach the undisturbed impact zone below. The success of the 2017 operation depends entirely on reaching the depths that previous teams either ignored or could not breach. The investigators prepare to break ground and dig precisely below the depth of the 1970s extraction. They must read the remaining subsurface soil profile to reconstruct the physical reality of the crash dynamics. The initial military salvage and the later civilian recovery were both influenced by a specific geological barrier beneath the soft topsoil. What physical forces shaped the remaining debris field hidden below the plow line? The crash geometry is confined to a shallow vertical band of around 6 feet, so the team plans for a heavily compressed impact zone rather than a deep shaft. In the soft topsoil, the aircraft could penetrate, but at roughly 6 feet, it met a hard sandstone layer at speed, capping further penetration and governing what survives for excavation. In effect, the hard sandstone behaves like an anvil beneath the soft soil. Field evidence is consistent with the engine striking that layer and being broken apart by the impact rather than drilling far deeper into the ground. The heavy forward structure appears to have dumped much of its energy into a hard, shallow floor, leaving the power plant shattered and scattered above the rock. Because the substrate completely blocked deep penetration, the bulk of the airframe was forced to collapse backward and remain exposed above the crater. This shallow stop helps explain why the 1940 clearance could remove major structure without deep digging. The modern investigative team must now interpret the permanent damage signature left on the sandstone floor. The team must adapt their current extraction methods to this highly compressed environment. Every fragment that survived the crushing force of the impact is packed tightly into the soil sitting directly above the rock. The soft earth is saturated with small, highly stressed metallic shards resulting from the extreme destruction of the engine block. The contrast between the soft, yielding topsoil and the hard sandstone base requires strict depth control during the modern dig. The excavation machinery can quickly peel back the upper agricultural soil, but it must not scrape or gouge the underlying rock layer. The excavation sequence relies on stripping the topsoil in controlled horizontal sweeps. The team constantly monitors bucket depth, so the sandstone is exposed cleanly rather than struck by steel teeth. That depth control protects the intact surface record at the base of the crater. Moving too fast risks scarring the sandstone surface that preserves the crash signature. At the bottom of the crater, the sandstone retains an immobile surface record of the impact zone. Investigators encounter a layer of staining on top of hard sandstone, accompanied by a strong smell of aviation fuel. The rock is also dusted with corroded and burnt aluminium, a residue the recovery team informally refers to as DAS. Together, these traces help define the lower limit of the impact area without claiming a precise chemical map of every internal failure. The staining and fuel odor indicate that petroleum fluids were present in the impact zone, whether as fuel, oil, or both. That evidence supports careful treatment of the sandstone surface as part of the site record, but it does not by itself prove the aircraft's exact running condition in the final seconds. If the modern heavy equipment breaches or scrapes the sandstone layer, that fragile surface trace can be erased. Therefore, the 6-foot depth limit acts as a hard physical stop for all aggressive mechanical digging tools. The team must carefully expose the anvil layer by layer to preserve the fuel staining and the microscopic aluminum dust embedded in the stone pores. The compressed nature of the site means there is no gradual transition from minor debris to heavy, intact structure. The investigative team is working directly downward into a high-density fragmentation field resting squarely on a hard rock floor. The sheer violence of the stop means that surviving evidence is likely to be severely distorted, torn, and folded back upon itself. The team must proceed with the assumption that the surviving metallic fragments are highly unstable. How do modern investigators safely extract fragments from this compressed damage zone? The primary hazard briefing for the excavation team centers on the possibility of 7.92 caliber ammunition within the debris field. Even decades later, ammunition and related items can present a safety risk, and licensed excavations are governed by strict stop work and reporting conditions if unexploded ordnance is suspected or discovered. At the same time, ammunition fragments and casings are contextual evidence of the 1940 combat loadout. The recovery team must maintain a controlled sorting logic that separates any ordnance-related material and other forensic micro-debris from the surrounding earth. Heavy machinery is required to move the sheer volume of soil, but excavators possess zero sensory feedback for small artifacts. A machine bucket cannot visually identify or tactily feel a small brass casing or a shattered aluminum bracket hidden inside dense clumps of wet topsoil. If the operation relied solely on visual spotting inside the main crater, they would inevitably bypass critical evidence and blindly crush live ammunition. To overcome that sensor limitation, the team splits the job, machine stripping for volume, and a separate fine sorting process for small metal fines. This workflow pairs careful machine stripping with spoil heap metal detection. The excavator removes soil in controlled lifts from the impact zone and places it in a designated spoil area, while detector operators scan that spoil for smaller metallic items that might otherwise be missed. When any suspicious ordnance-related item is encountered, work is paused and handled under the reporting conditions that govern license recoveries. This approach slows the dig, but it improves evidence capture in a site that has already been harvested, and it reduces avoidable risk while heavy equipment is in use. The team trades time for physical control over the debris field. The spoil heap detection method ensures the upper agricultural layers are thoroughly sanitized of historical artifacts. The mechanical layer stripping efficiently handles the scattered, isolated fragments suspended in the soft earth. The operators establish a rhythm of sweeping, dumping, scanning, and clearing. This dual method works only while targets remain small, disconnected, and suspended in the soil. Deeper down, the debris begins to resolve into coherent structure, and the bucket itself becomes the risk. The operational edge of the excavation hinges entirely on recognizing the exact moment when the primary extraction tool becomes a direct threat to the forensic evidence. Heavy machinery provides the sheer lifting power required to strip the disturbed upper soil, but an excavator bucket operates with immense hydraulic force. If the steel teeth of the bucket engage a thin, walled aluminum structure, the machinery will shear, crush, or deform the metal before the operator even registers the contact. This rigid constraint forces a definitive trade-off between extraction speed and physical preservation. The team must identify the transition boundary before the equipment destroys the historical integrity of the crash site. This boundary is reached at around 2 feet. As the mechanical bucket skims away another shallow layer of earth, the visual profile of the wreckage changes. The isolated metallic micro-debris gives way to coherent, recognizable aerodynamic structures. The operators halt the heavy machinery upon sighting the distinct shape of a rudder mass balance weight and a recognizable section of a tailplane rib. The discovery of these aft components at the 2-foot level triggers an immediate shift toward hand excavation to protect fragile evidence. The sudden appearance of structured debris forces the complete cessation of mechanical layer stripping inside the primary crater. The operational mandate immediately requires a transition to hand excavation. The team cannot risk another blind bite of the agricultural soil. The structural remains of a fighter aircraft, particularly the tail assemblies, are constructed from lightweight, thin, gauge aluminum framing designed for flight, not for absorbing heavy localized point loads. Using an excavator to dig blindly into the structural matrix would irreversibly scar the metallic surfaces, warp the aerodynamic profiles, and obliterate any battle damage signatures hidden beneath the dirt. The recovery personnel physically enter the shallow crater to assume direct manual control over the extraction. The heavy tracks of the excavator are parked at the staging area, and the team deploys hand trowels, brushes, and specialized digging tools to work directly around the artifacts. This manual transition fundamentally alters the geometry of the work site. The excavators are no longer looking down at the earth from a distance. They are working inches from the metallic fragments, carefully peeling the soil away from the surface of the aluminum. The earth must be removed laterally, undercutting the artifacts to expose their edges without applying downward pressure. This strict hand troweling protocol proves critical as the manual digging progresses downward to a depth of 3 feet. At the 3-foot mark, the careful scraping reveals a large radiator section buried alongside the tail components. The cooling matrix of an aviation radiator is extremely fragile, consisting of hundreds of thin metallic fins easily crushed by the slightest external force. Had the mechanical excavator continued past the 2-foot boundary, the steel bucket would have violently compressed the radiator matrix, destroying its physical shape and eliminating its forensic value. Hand excavation allows the team to map the contours of the radiator and clear the dense, packed soil from its delicate fins without causing secondary structural collapse. The hand excavation process also requires careful stabilization logic. As the earth is removed from around the tailplane rib and the rudder mass balance weight, the items lose their physical support. The team must clear the dirt evenly along the length of the components so they do not bend under their own unsupported weight during the extraction process. Once fully exposed, the team lifts the artifacts free from the 3-foot layer, ensuring that any sharp edges or torn metal boundaries are protected during handling. This slow manual phase removes the fragile tail components without adding fresh deformation. Once cleaned and stabilized, the rib can be read for damage signatures that the archives alone cannot settle. The current physical state of the recovered artifacts provides the foundation for forensic verification, while the precise sequence of the 1940 destruction remains locked in the historical archives. The procedural mandate for the investigative team is to match the newly stabilized metallic evidence against the established documentary record. Documentation associated with the loss is described by the excavation team as consistent with anti-aircraft fire. Other compiled accounts of the same pilot and airframe describe aerial combat over England, followed by a forced landing in the same general area. That tension is exactly why the metal matters. The investigators are not treating paper as gospel. They are asking the recovered structure to confirm one hard fact. The aircraft sustained battle damage in flight. The puncture geometry on the tailplane rib is consistent with a high-velocity projectile strike, supporting the presence of combat damage without overclaiming the precise source of fire from a single surviving fragment. Mating the physical evidence to the archival record fulfills a critical operational objective. It transforms a highly disturbed, heavily diluted crash site into a verified historical engagement scene. The recovery team has successfully extracted a definitive truth from a few square inches of surviving metal, bypassing the massive gaps left by decades of earlier salvage operations. The tail section has yielded its final piece of data. However, the tail components only represent the upper structures of the failing aircraft. While the combat damage is now confirmed, the team must still map the absolute limits of the physical destruction. The final phase of the operation requires the investigators to return to the crater and clear the remaining dirt from the deepest point of the impact zone. They must document the exact termination point where the heaviest mechanical assemblies finally stopped moving. What condition marks the absolute bottom of the excavation sequence? The investigation reaches its final physical limit at about 6 feet below the surface. This boundary is defined by a hard sandstone layer, capped by a stained zone with a strong smell of aviation fuel. In that lowest band, the team recovers minor engine components from the saturated soil immediately above the rock. Among the small finds documented from the dig are 4 engine valves, later cleaned and preserved, alongside other fragments from the shattered power plant. Reaching the sandstone and the natural ground beneath it signals the practical end of productive excavation at this site. With the remaining solid fragments lifted out, the sandstone floor is exposed in full daylight. It is deeply fuel-stained and carries a fixed white residue of oxidized burnt aluminium, days worked into the rock pores over decades. Unlike the loose fragments, this chemical footprint cannot be lifted or preserved outside the ground. That immobile boundary sets the termination criterion. Digging into the sandstone would produce no further aircraft structure and would only erase the surviving surface trace, so the excavation is formally closed at the rock floor and heavy tools are stood down. The overall operation concludes as a measured success, constrained by what earlier recoveries already removed. The investigators extract key items and document the site's hard geological limit. However, decades of earlier clearance impose a hard-proof ceiling. Most of the main airframe and the heavy engine mass were removed long before this licensed dig. The team's success is therefore measured in what survived below the plow line, documented fragments and a defined impact limit, rather than a complete structural recovery. Following the strict remediation requirements of the Ministry of Defense license, the team initiates the site restoration phase. The operation pivots from extraction to environmental repair. The heavy machinery returns to the edge of the crater to begin the backfill sequence. The earth that was previously removed, spread thinly, and scanned at the staging area is now pushed systematically back into the void. This loose, sifted soil cascades down to bury the fuel-stained rock and the white aluminum corrosion once again. The operators carefully level and grade the fresh earth to seamlessly match the surrounding terrain. The physical metallic evidence is safely secured and packaged for permanent historical preservation, while the site itself is returned to its standard agricultural grade.